This is the theory called the proton-proton chain reaction, the theory that tells us where the energy comes from that powers the sun. When you're looking at all of this, I expect that you're probably wondering, oh my gosh, do I have to memorize things like that for the exam? I don't like you to memorize things that you don't understand. What I want you to get out of this is I want you to understand, what does it mean to be a chain reaction? And when you look at these steps of the chain reaction, I want you to understand that every time we do one of these fusion steps, we are creating new things coming out of the fusion process. Can any of these things actually be seen or detected so that we can test this theory? Because this is a theory that somebody had to work out in order to figure out where the extra energy comes from that powers the sun. But is it the right theory? You know that when we're done with a theory, we want to have confidence in it by doing some sort of tests, some sort of new observations that will give us that confidence. So try and retain those kinds of ideas of what comes out of this reaction and what comes out and goes back in. So let's start here. What is a chain reaction? A chain reaction is when you start with certain kinds of materials, in the case of fusion, certain elements like some hydrogen, and this goes through several steps of a process, and you get to the point where you have actually gotten some of the things that you started with coming back out of the process. Not all of them, but some of them. So in this proton-proton chain reaction, which says proton-proton, but which means hydrogen-hydrogen, same thing. 6 hydrogen are going to go in once we're done with all of these steps, and we'll get to the end and we'll see that 2 hydrogen actually come back out of the whole process. Well, that's great. I would like a car that does that. I would like a car where I put 6 gallons of gas into it, and then I put a bucket on the exhaust pipe, and by the time I've burned through those 6 gallons of gas, I got 2 gallons of gas that came back out. So I can go and pour it back in the engine and go through it again. That would be great. And that's what a chain reaction does. It doesn't necessarily use up all of the fuel. A little bit more of that fuel comes back out and can be part of the next process. Now, the first part of this process starts with 2 hydrogen, in other words, 2 protons, that are going to smash together and form a deuteron and a positron and a neutrino. Well, that's just exactly what we just described in the previous slide in more detail. So we've already gone through this part, all right? We've gone through 2 protons collide together, make a deuteron, out comes a positron, antimatter, out comes that new neutrino particle, which has very little mass. So we've done that one. What's next? You made a deuteron. Here's that deuteron. Here's another hydrogen, a third hydrogen that's coming along, and it's going to smash into that deuteron. So when this hydrogen smashes in with this hydrogen nucleus that's got a proton and a neutron, they go off together with 2 protons and 1 neutron. Now that you have 2 protons together, you've made a helium. But you only have 3 pieces there in the nucleus. That's going to be helium-3. Now, other things come out of this, and this equation is showing a Greek letter gamma. That is actually a gamma ray. That is part of the electromagnetic spectrum. That's the highest energy part of the electromagnetic spectrum, more energy than X-ray. So the sun is producing these gamma rays inside of its core, and those gamma rays are going to try and come out of that core at the speed of light. But the center of the sun is so densely packed with all of that hydrogen that it's going to take a while for that gamma ray to get out, because it'll keep colliding with hydrogens and being absorbed and then re-emitted, and then it's absorbed and re-emitted again. And every time that it's re-emitted with a little less energy, which means even the gamma ray is a way of disposing of energy into the sun and giving energy off to the particles, and it helps heat up the sun. This capital E in the equation is also telling you that there is extra energy produced in this fusion process. So here's where E equals mc squared comes into play. And where does that energy go? It goes into this helium atom that's just been formed. Now that has a lot of extra energy as it's being born, and that's a high energy particle, which means it has more kinetic energy and therefore is providing a particle that's more heat in the core of the sun. We have just made heat in the sun when we did this step, and you recognize that by seeing the capital E. So now you've made this helium-3 particle. It's hanging around waiting to be a target. Oh, but wait, here comes another one. So two helium-3s are now going to smash together. Where'd the other one come from? Well, you did these two steps once to make a helium-3, so you have to do these two steps twice to make a helium-3. So if you're going to go through these steps twice, how many total hydrogen go into making enough helium for the third step? You have to do 1, 2, 3 hydrogen, and then you have to do 1, 2, 3 hydrogen again to make 2 of these helium-3s. How many total hydrogen was that? That was 6. So now 6 hydrogen total have gone into the process by the time we're down here and putting together 2 helium-3s. And they come together and they smash together, but they don't smash together to form a particle, to form an element that has 6 pieces to it. No, these hydrogens are going to come flying out of this process and leave you behind with a nice, stable, regular helium-4. So, helium-4 is made, but extra hydrogen now come popping off of this also. These are the 2 extra hydrogen that are now coming out and being freed up to go back into this process again. 6 hydrogen went in, and now 2 hydrogen are coming out in the very end of the process. And there's a capital E. Remember what a capital E means? E equals mc squared just happened again, and these particles, any of these 3 particles, can carry away that extra energy and go out there and be extra hot for the next step. So, what do we want to take away from all of this? This proton-proton chain theory of how the sun is powered has these results. Hydrogen in the sun, and it has a lot of hydrogen, is being turned into helium-4. Eventually, you should be able to turn almost all of your hydrogen into helium-4. And after that, you're going to say, then what do you burn? Okay, that's for a future story. Extra energy is being released to power the sun. E equals mc squared. When we saw those capital E's, we now understand where the energy comes from that heats up the particles that are making the sun so hot. And there's another thing we weren't necessarily expecting. Gamma rays are going to be coming out of the sun. They're going to try and push their way out of the center of the sun, but they keep colliding with other particles on their way out, and they lose energy to those particles. That means the particles are gaining that energy, and therefore they are also hotter. Gamma rays help to heat the sun, starting from the inside and doing less and less as they work their way out. And then also, there's these little neutrinos that are made. Now, I didn't tell you too much other detail about the neutrinos before, but gamma rays, remember, are very penetrating particles from the electromagnetic spectrum. They're coming right through our atmosphere and shooting right through our buildings, and then they're going down into the earth. The neutrinos, even though they're not part of the electromagnetic spectrum, are very energetic particles with very little mass, and it's very hard to absorb them. So they come easily flying out of the sun. And they come flying out to Earth and come through our atmosphere and our buildings and go down into our Earth, and they can go through the Earth. Now, if you ever want to try and capture a neutrino, you're going to have to put something in its way at just the right time so the neutrino would absorb into it and react with it. And that would have to be something which has higher density. like the Earth itself or like water, but the atmosphere is relatively thin, doesn't capture many neutrinos. Okay, so it is possible to capture them. You just have to give them more opportunity. Otherwise, they'll just happily fly through the empty space of atoms and keep on going. Now, I have had people say to me, oh my gosh, sometimes I think about what if I wake up the next day and the sun has burned out. Oh, no, 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 don't worry about those kinds of things. Okay? The sun has enough hydrogen to burn for 10 billion years as a regular star. And actually, we're probably about halfway through that. So we still have another nice 5 billion years next to go. Okay? So there's plenty of hydrogen up there for the sun to burn. No worries about it burning out.